channel, and today I'm going to be talking about calculus problems in review, and this is the second part. So earlier we released a video and it was talking about calculus and problems, and we're doing some review, and we're going to continue with that. We did 3 problems last time: a derivative problem, an integral problem, and a limit problem. And today we're going to be solving 4 other problems: 2 on partial differentiation, 1 on integration, in which we're observing the fact, and the last one is a bonus, which is higher than calculus, a differential equation. And this is a linear differential equation. So let's begin. So first we're going to be dealing with partial differentiation. So partial differentiation. So what does partial differentiation mean? Well, so for example, let's take physics. In physics, we have the Schrodinger's equation, which involve partial differential equations, and so on and so forth. And in the sciences especially, and even in pure mathematics, we have multiple variables. And say we want to differentiate this for a reason graphically or analytically, what happens is that we are going to differentiate everything. But we don't want to differentiate everything. We only want to differentiate the thing that we're taking with respect to, which is a main variable. But how do we do this? Well, we treat the others as constants. So we take the derivative of the variable which we want and treat the other variables as constants. This is going to be called partial differentiation, whereas implicit differentiation doesn't treat the other variables as constants, it does differentiate them. So today we're going to be doing some partial differentiation problems. So let's start with the first one. We have the partial derivative with respect to x of 7x squared plus 9xy minus 2y plus 7y squared. Okay, so we're going to be solving this problem. So let's first take the derivative with the x terms. We have an x term over here, so 7x squared. Well, the derivative of that is, we can use the power rule, which is nax to the n minus 1. If we substitute, x will just be x squared minus 1, and then 7 times 2, so 2 times 7, so this will be 14x, and then that's going to be it, so we get 14x for the first term. So we can write 14x. Now for the second term, we have 9xy. Okay, so some people might get stendo here. They know that we have to treat y as a constant, but they're like, okay, how do we do this? Well, imagine this. So we have 9x2. And y is not 2 in this case, we're just giving a demonstration. Well, how would you simplify this? From algebra, we know this is just 18x, because this is multiplied, and the commutative property of multiplication, and we can just switch this order, and boom, we get 18x. And this is essentially the same thing, because we get 9x times 2, 18x, or 2x times 9, which is also 18x. So this is what we get essentially. And if we treat y as a constant, we're going to get that too. So we only need to differentiate with respect to x. So what we need to do is take the derivative of x. Well, what is x? Well, x has no power. Well, it does have a power, it's 1, but it doesn't have any higher power other than 1 or lower power other than 1, it just has 1. And the coefficients are 9 and y. So 9y times x. Well, the derivative of x is obviously just 9y. Well, the derivative of x is just 1, and we'll just get a 9y as the remaining. So we're just going to add 9y. Essentially how you would treat the same thing. So if we have 9x and then 2, which is just multiplied by everything, we take the derivative with respect to everything. Well, if we take the derivative, this will be 1 times 2 times 9, it will just be 18. So that's essentially that. And you could also think of it this way. So if we take 9yx, you can treat this as the coefficient, and when you take the derivative of x, this is just 1, so we just get 9y essentially. So we get 9y, so we solved our first 2 terms. We've got our first term, our second term. Now we have to do our third term. Well, we have minus 2y. Well, how do we treat this? Let's get back to our 9x2 example. Let's take the x away and just put 2. So say we have 2 times 9. So we have minus 18 in this case. What do? Well, if we have minus 18, we know from basic derivatives or differentiation, we know that when we take the derivative of, say, a constant, then what happens is we're going to get 0. This constant just eliminates. So if minus 18, which it is a constant, then this just has to eliminate. So when we take the derivative, these terms eliminate. And we're treating y as a constant, as that's what partial differentiation means. So when we treat y as a constant, what happens is this will just become 0. So we'll get minus 0 plus 7y squared. Another term that has no x term, so this has to be 0 too. And obviously minus 0 of this two terms is just going to be 0, but you can just cancel this out. So essentially we'll just get 14x plus 9y. So we solved our partial derivative. So the partial derivatives looks hard because of the symbols, essentially. The symbols, which is just this symbol, and then over the variable you're differentiating with. And it can also be like dy over dx. You could do that too, but essentially you would just replace these with these symbols. But right now we're going to do this. So this is essentially how we're going to be solving this, and we have just done partial differentiation. So partial differentiation involves many things. So when you're doing partial differentiation, you could take partial differentiation and graph it. When you're graphing it, it becomes a very cool graph. And essentially, partial differentiation has a lot of applications in physics, like the Schrodinger's equation. And partial differentiation can be graphed or calculated analytically. So we just did it numerically, and we got our answer. So we got 14x plus 9y. So let's check our work. 7x squared, that's 14x, first term. 9xy, if x is the one we're differentiating for, then it'll just be 9y, and we are. These two terms will cancel out since they have no x terms. Boom. So we get 14x plus 9y, and we can write this in our answer box. We get 14x plus 9y. So now that we have done this, let's look at our second problem. So our second problem involves z's and r's. You usually have z, x, and y, and remember, when we're dealing with partial differentiation, we can get for systems of 3 variables, or maybe even 4 variables. We just don't need 2 variables. We can have any number of variables, but it's essentially just the same thing. So if you have 9 x, y, z, this will just be the derivative of the x is 1. So this will just be 9y, z. So this is essentially going to be it. So it follows the same rules. So now let's do the second one, or technically the fifth one in this case. We have the partial derivative with respect to z. And we're going to have 3z squared plus 9r squared minus 2z squared r squared. So minus 2z squared r squared. Okay, so we have 3 terms over here, and one of the terms looks fairly easy. Well, we don't have a z term over here. So what can we do? Eliminate this. So this will just be eliminated, so we can cancel this out. So we'll just get the partial derivative with respect to z, and then we're going to take 3z squared and then minus 2z r squared. And remember, this and this are not equal. What we're just doing is, now that we've canceled that out in our partial differentiation step, we can take the partial derivative of these separately. But these two are technically not equal to each other. So now what happens is minus 2zr squared. Well, let's do 3z squared first. And remember, z also has to have a squared over here. So we're going to have 3z squared. Well, this will just be 6z. And we can check if we integrate this, this will be squared over 2. So we get 3z squared essentially. So this will essentially just be 6z. And we're going to have the partial derivative of minus 2z squared r squared. So remember, always look at the problem carefully. So we're going to have minus 2z squared r squared. So how are we going to be doing this? Well, to do this, we can write it over here. Minus 2z squared r squared. So this is our first step. Write it in a clean space, because when you write it in a clean space, you can obviously find the answer quicker. Now, we're taking the partial derivative with respect to z, right? So now take the derivative of z squared. So we take the derivative of z squared. We obviously get 2z. So now that we get 2z, we can just essentially multiply. So we get the derivative of this is 2z. So if we just group this over here, so z squared, and then minus 2r squared, all multiplied, and this will just be 2z times minus 2r squared. This will essentially just multiply to get minus 4z r squared. So we'll get minus 4z r squared, and this will be our answer. Okay, so some people might be confused about this last step. So they know this will cancel out, they know how to do this, but what about the last step? How does it cancel? So let's take an analogy without two variables, and let's just say we have x. And x is the best variable, and now what we're going to do is we put x over here, and now let's say let's put x squared, and let's put two other numbers. So we'll get minus 2, let's put 9. Well, if we get this will just simplify, right? And once we simplify it, so let's just say we simplify it, and we'll get minus 18. Minus 18x squared. And what we can do is essentially, this is nax to the n minus 1. We can take 2, multiply to get minus 36x, and that'll be our answer, right? Well, essentially, except this 9 is going to be our r, which is r squared in this case. But what happens is, 9 is not equal to r specifically, we're just making a random example, but essentially this is what's going to happen. We're just going to get our answer over here. So minus 4z r squared, and the reason we have r squared is because r squared is one of our terms, and we can't differentiate r squared since that's not allowed. So essentially, this will be our answer to this top term. And remember one thing, that these two things are not equal. When we cancel this out, essentially, in our process, this will just cancel out, so we'll just get this, and this is just a tiny function, which is easier to process than this big function. So now that we have done this, we can just label it over here. So we get 6z minus 4z r squared. So now that we have done this, let's work on our new problem. So our next problem is integration. And integration, we're not going to be computing anything. Well, we first have to compute something, but then in the next step, what we're going to be doing essentially is we're not going to compute, we're just going to observe. Okay, so let's take, we have the integral of 2x over x squared. What is the answer to this? Well, the top of your mind should say the natural log of x squared. And if this doesn't say to you, and we can just put parentheses over here, so natural log of x squared, and then plus c. Okay, so why does this equal? Well, if you forgot probably your integration techniques or just learning it, this is very easy. So say we have, so if in differentiation probably you have learned that 1 over x, well, if we take the natural log of x, say we have the natural log of x, this is just equal to 1 over x, so when we take the derivative. We know this from differentiation, and this is probably a right-hand trick and rule which we know. But say we have the natural log of f of x, which this is essentially, it's just f prime of x over f of x. So if we have this essentially, this specific pattern, we know that we get this. And when we take the derivative, we get this. But when we take the integral, we get here. So that's essentially this term for the integral. And instead of writing f prime of x, what we just did is put the derivative of x, essentially. And now, we can just observe that any specific place in which we have this term, essentially we convert to this. So now that we have done this, let's observe some more properties. So say we have the integral of 9x over x squared plus 7. And we've already solved this, and we got 9, the natural log of x squared plus 7 over 2 plus c. So we already did this problem essentially, and we got our answer. So why are we talking about it again? Well, for our observation. So if you look at this problem more deeply, we have the natural log. And when we have the natural log, this is important. The reason why is because what we're trying to do essentially here is we're trying to convert this numerator so that it becomes the derivative of the denominator. Essentially, so we're going to have dx over x is going to equal the natural log of x. Let's see. So we know that this and this are equivalent, so that's where we're going over here. So that's why we have the natural log of x squared plus 7. What was the problem? 9x is not the derivative of x squared plus 7. It's 2x. So what are we doing? Well, we're essentially putting it 9 halves of x, because when we're taking the derivative, essentially, we're just multiplying. So if we do compute this, we're making a u substitution. U is equal to x squared plus 7. du is equal to 2x dx. And when we plug it in, we can just multiply. So if we have 9x, and then over x squared plus 7, and we substitute, we can get this to be u. And for this to be du, we have to multiply by 9 halves, and we get du. So essentially du over u. So part of this and this, we'll get it, and we'll get a coefficient of 9 halves to make this inequality true. Well, not inequality, this equation true. And then essentially we put the 9 halves over here, and that's how we get this. So right now in this integral, if we were to explain it more deeply, what we're doing is we're trying to make the numerator the derivative of the denominator. So therefore, we did do it, and we put a fraction 9 halves, and we got it, and we got our answer. So this is one important thing to notice about integrals and derivatives, essentially. Well, we picked integrals because it would cover the topic of derivatives, and integrals are very cool. So now, let us go to a differential equation. So we have a differential equation here, and if you're doing regular calculus class, you probably won't be taught this, or you could learn it ahead. So we have this dy over dx, and this is not a related rates problem. And we're going to add sine of x is equal to cosine of x. What is y? With some intuitive thinking, if you're really smart, you could probably get the answer to this, but without intuitive thinking, you probably can't get the answer to this. And how we do it is we use the integrating factor. This is a linear differential equation, so we can use the integrating factor, which essentially is e to the integral of p of x. And the form of this is y prime plus p of x. Oh, we also have to add a y over here. So if we add a y to make this a linear differential equation, we can have a p of xy is equal to q of x. We essentially have to put the integrating factor e to the integral of p of x over here. And what's p of x? Well, p of x is sine of x. So the derivative of the integral of sine x is going to be e to the minus cosine of x. So the integral of sine x is minus cosine x, and the integral of cosine x is sine x. So we know that we have e to the integral of cosine of x. When we multiply, we're just essentially going to get e to the minus cosine of x y is equal to the integral of e to the minus cosine of x times q of x, which is cosine of x. And essentially we get that. Now if we divide by e to the minus cosine of x, divide by e to the minus cosine of x, we get our answer, which is y. So this is essentially how you solve it, and you could simplify more, but we're just going to leave it over here. So we can write e to the minus cosine of x, and we have to put the integral sign all over e to the minus cosine of x must be equal to y. So now that we have finished our problems, we can conclude that we have covered most of basic calculus and most of advanced calculus, and we're going to post more future videos specifically on derivatives as a review and integrals as a review. But this was just a basic reviewing, and please watch the first part if you want to learn more about this one, because this involves most of the rules from differentiation. This is just basic, which we just covered, and we covered limits too. So if you like this video and if you like this channel, please subscribe to learn more. Thank you.